squared, right? So why this is the case? So if we have a shaft down here, right? And we know that over here, if our moment is acting in this direction, right? So we know that the distance from here to here is equal to c, right? So y is equal to c when where stress max will occur. Okay, so I'm going to call it c. That's why we move the equation over there. So you have now equal c over j square root by m squared plus by t squared. Okay. And take note, so take note regarding this. So take note that m is equal to my squared plus by mz squared. And this is only for a shaft, yeah? For shaft, you can use this relationship, okay? Why for a shaft, you can use this relationship? So for a shaft, we know that Izz is equal to Iyy, okay? The second moment of area in the yy axis and z axis are the same for the shaft, okay? So we can finally use this relationship where j over c, right, is equal to, so m squared is equal to my squared plus by mz squared plus by torque in the x direction squared divided by tau max. Okay, so from here, from this relationship, you can calculate, okay, we can calculate the radius of the shaft. Okay, so that's how we combine that's how we combine the stresses in the normal and shear together with the material behavior, material properties, because the tau max over here, right, this value over here is a material property. Okay, where these values over here, all this is from your structure analysis. Then you can specify the shaft that you're going to size, okay, based on the loading. Okay, so if that's the case, anyone, any questions, please? Anyone? Well, okay, right. So we are going to go into example number 1. And this is an example, I'm going to go slow. As I said, the last time when I taught this course in the winter, a lot of students are not able to do this question. And they cannot do this question not because they don't know what formula to use. It is the analysis. Nothing to do with the formula. The formula is so straightforward, right? This is the only formula that you need. Okay, it's so straightforward. Is the analysis, okay, that's going to cause a lot of problems. Okay, so as I said, the last time I was not very successful. Okay, I hope to change that. Okay, right. So let's look at this problem now. Okay, so we have a so there's a lot of information that is that's needed to design a shaft. Okay. Okay. So this is our system. So the solid shaft AB rotates at 480 RPM. Okay. And then it transmits 30 kilowatt of power from the motor M. So from this diagram we can see that M specify the motor, right? connected to gear G and H. So we have gear G and we have gear H. And 20 watts is taken off from gear G. Okay. And 10 watts is taken off from gear H. So this motor, it transmits, so input, right, is 30 kilowatt, right? And the output, right, the output, so G will take 20 kilowatt. So G will take out 20 kilowatt. So output, so the output to gear G is 20 kilowatt. Oh, hold on. And the output to gear H is 10 kilowatt. Okay. And knowing that the shaft, the material, so we are given that the material we can choose, the allowable is 50. Okay, the allowable shear is 50. Determine the smallest size of the diameter for shaft AB. So what is the minimum diameter of the shaft we can have on AB? So the first thing we have to do, okay, is to analyze the direction. Okay, analyze the direction of the forces. Most important. If your forces is wrong, everything is wrong. Okay, so the forces it control. So the force is controlled okay, the force is controlled by the gear that is linked to the motor. So we usually call it the driver gear. Okay. Okay, we usually call it the driver gear. Okay. So now the first thing I want you to look at, right? I want you to look at this diagram over here. And I want you to watch the direction of the motor. So I'm going to copy this diagram again. Oh, it's doing weird things. Hold on. Okay. So as you can see over here, right? The motor is rotating in if we view from, if this is our orientation, so this is X, Y, and this is Z. And if we view from point X, right, where the gears touches is where the force will react, or the force will be transmitted. So for gear, the motor gear, the force is going to act in this direction. Okay, the force is going to act this direction. Okay. So gear E will also rotate in the same direction. Okay, so this will be how the force at gear E will move. Okay, so if you see the direction, we know that this gear will rotate, gear E will rotate in this direction. So if gear E will rotate in that direction, gear D will be in the same direction, and gear C will be in the same direction. So for this case, gear E is the driver on the shaft. Gear D and E, C and D are the driven. Okay, these are the what? Driven. Okay. So the force, the first thing you have to take note, the force, okay, the force acting position is located where two gears are in mesh. So what do I mean by that? Okay, so you look at force E, right? I'm drawing force E exactly where? Exactly at the point it intersect the engaging, or where it intersect the what? The two gears. Okay, so that's where I drew my arrow, right? So for gear H, okay, or the driven gear D, so let's focus on driven gear D. How this will react, right? It will react in this direction now. Okay, it will act in this direction. So this is my, that is so bad. Okay, so you will act in this direction. Same thing. I think I'm colorblind. I thought I selected pink, and so this will be your, it's okay. So this is your force of your D. Okay. So I drew over there, first of all, the position. Right? What did I say? The first thing is it will initiate at the point when two mesh are in what? Like I just highlighted in yellow, right? Where the two gears are meshed together, and that is direction. Okay, now let's talk about the direction of the force. So we know that force E will be coming downwards, right? Okay, so I'm going to view this in a different orientation now. I'm going to view this in the, so this is my Y, and then this is my Z. Okay, this is my Z. So I'm going to draw my first shaft. So that it will be my gear E. So this is my, I'm going to draw in light because it's not really important. So this is my gear E. Okay. And that is my gear of the motor. I'm going to draw the gear of my motor. So this is the gear of my motor. Right. And these are the axes. So we know, right, what I just specified is we are aware that this is coming down. This is a force at point E, right? And this is our gear E. Right? And the shaft, all the gears, every gear will rotate in this direction. Okay, so this is our rotational direction. Because it's given to us, the motor gear is in this direction. Okay, so this is the motor gear. So gear E, I call it the driver. Okay, because gear E is the one that is driving our shaft. So what do we want to calculate? We want to calculate what? We want to calculate what is the diameter of this shaft. So this is the important part. We want to know what is the diameter of this shaft. Okay, so this is the shaft. Right. So let's now focus on gear D. Okay, so now let's look on gear D. Okay, so gear D is slightly smaller. Okay, so this is our gear D. So I'm going to just sketch gear D. So this is our gear D, right? Now gear D, right? It will engage another gear at gear H. Okay, so this is